Okay. Numbers 4 and 6. Let's see what we got here. Oh, this is a good one. I like this one. Okay, yeah. So, let's see. For the block, right, the total kinetic energy is just translational. So it's going to be 1/2 mv squared, right? And that's it. For the cylinder, yeah, cylinder. So we could generalize this to any kind of object that's rolling, really, right? If we know the moment of inertia for it. Remember, the total kinetic energy is just going to be the translational kinetic energy plus the rotational kinetic energy. So the block and the cylinder have the same mass, right? So this 1/2 mv squared term will be there for the cylinder because its center of mass is translating, and then it's going to have rotational kinetic energy too, right? Because it's rolling. So 1/2 I omega squared. We use the no slip condition. Yeah, we can do 13 and 18 next. No slip condition, right? Remember, which is pretty important. Gives us that V is R omega, right? We want to just get everything in terms of probably M and V here. I mean, that's all we can really do. So we say that omega, right, equals V over R. The moment of inertia of a cylinder is I equals 1/2 mr squared. So then plugging this all in, we get that the total kinetic energy of the cylinder is 1/2 mv squared plus 1/2 I is 1/2 mr squared. You have to be careful with cylinders in particular, right? Because the moment of inertia formula has this 1/2 out in front, so it's easy to forget about this extra 1/2 from the rotational kinetic energy. So just be careful about that. And then V over R, quantity squared, right? So we see that, like with the other one we were looking at from the Hattridge's practice exam, that the R's end up canceling out, right? So this becomes 1/2 mv squared plus 1/4 mv squared. Right? Yeah, I think that's good. And so then it's 3/4 mv squared. So then we take the ratio, right? So the cylinder over the block, and this works out to be 3/4 mv squared all over 1/2 mv squared, right? So the mv squared terms cancel out. We get 3/4 times 2, right? Which is 3/2. Yeah, 3/2. Cool. And so the important thing to note about this one, I think, is that we can always, for all the common objects that we might encounter, right, just write the moment of inertia as some numerical coefficient times mr squared, right? And this is what I did for the other problem. And in that way, for like an object that's rolling, right, rolling along so that it's spinning about its own axis and its center of mass is translating, we can always basically just come up with some expression for its total kinetic energy that like just depends on some factor in front of mv squared, right? So that's kind of useful to remember, I think. Does that all make sense? I'll move on to 6, but we can come back to this if there are questions. This is another, I think, good one to make sure that you're clear on. Let's see here. So we could just brute force this, right? The first thing to note is that it's a point mass, so it's not going to be spinning about its own axis, which means that like it won't have any spin angular momentum, right? It'll just be the orbital angular momentum. So we can say L equals R cross P, or well, not MP, R cross MV, right? Which is P, is just the linear momentum. This is a vector. So what this ends up looking like is we can take a cross product of two-dimensional vectors as long as we just sort of force them to be 3D before we do it, right? If we want to do it that way. And so for R, we can write its x component is just 3 meters. Its y component is 2 meters, and it has no z component because it's sort of restricted to the xy plane just by the problem statement. And then we times 0.1 kilograms times the other vector, the velocity vector, which is pretty nice because it only has one component, right? Just the y component. And so it just comes down to evaluating this. Alternatively, right, you could just evaluate R cross V and then remember to multiply whatever you get there by 0.1 kilograms because that is fine. That's a property of the cross product that is okay to use, right? You just pull some non-vector constant out front, and it doesn't end up really mattering when or where you multiply it because kind of everything gets multiplied by everything, right? So let's just do this. And I mean, we kind of know, right, that from our intuition about the cross product that this angular momentum vector is going to point in either like the positive or negative z direction, right? Because the r vector is in the xy plane and the v vector is also in the xy plane. Let's see what we get here. So it's just going to be a negative 1.5. What are the units here? Well, kilograms. We have meters for R. And then meters per second for V, right? So it's kilogram meters squared per second. Yeah. That should be good. Like this. And let's just put z hat in there so we are clear that it points down, but we probably all see that at this point. Z hat. Okay, so 4 and 6. If these are good, then I can move on to 13 and 18, which were the other ones being asked about. Okay. So I think that like Jackson in the GroupMe found a way to program the cross product into your calculator if you want to do that. And this kind of just makes it pretty easy to do something like this. But also, you could just have drawn the vectors, like made a sketch of what they look like, and then use the right hand rule and like the definition of the cross product being just the product of the two magnitudes times the sine of the angle between them, right? So that's another way to do this. Okay. 13, let's see what we got here. Certain simple pendulum oscillates with frequency omega near the surface of the Earth. The period of its oscillations beyond the surface of the Moon. Okay. I don't remember the formula for simple pendulum. I think it's like the square root of g over L or something pretty straightforward, but let me just double check this. The frequency of simple pendulum. Yeah, it's just g over L. Square root of g over L, right? Yeah. Okay, so what we do is we just say omega equals square root of g over L, right? Just saying that like the pendulum obviously has some length, or the string that we're using to make the pendulum obviously has some length. So I would say it couldn't hurt to have the cross product thing on your calculator for the final. Okay, so what we do, right, this is not that different from the exam problem where you had to just like figure out what the spring constant was, or rather what like the angular frequency was in terms of like a different sort of set of masses and spring constants, right? Is we just say, well, then omega prime, right, it's just going to be the angular frequency on the moon, is going to be g prime over L, right? So the only thing that doesn't change here basically is L. And g prime is, as we're told in the problem statement, just g over 6, right? Because it's 1/6, 9.81 meters per second squared, whatever that comes out to be. And so we could write that this is g over 6L, right? Now, the equation for the period was like something like t is 2 pi over omega. And so what we do is we just say 2 pi, wow, okay, third time's the charm, divided by the square root of g over 6L. And I think that's all there is to this, right? So just remember, right, that omega prime is the angular frequency on the moon. G prime is the moon's gravitational acceleration. And we'll get a number here in short order. Oh, wait a minute. We don't have L though, but that's okay. I think that's fine. I'm not being as careful here as I should be. So what the step that I was missing is we need to pull out this 1 over the square root of 6, right? I was like about to get the number and I was like, wait, we don't have the length. So this is what I had intended for you to do, right? Is to note that omega prime is just 1 over square root 6 times omega, which is known, right? It's the 0.225 radians per second. Or actually, you could have just used this to get the length too. So either way, it's fine, I suppose. You get, however, this is nice because we have this value already, right? So you get that it's omega over the square root of 6. So what we do is, this should be omega prime. I'm just getting warmed up, okay? Is 2 pi over omega divided by the square root of 6. And this is what you were supposed to do. So we can now calculate this. 2 pi over 0.225 times the square root of 6. And I'm getting that it's about 11.4 seconds. Okay, hopefully that makes sense. Like I said, you could have done two things, right? You could have solved for the length, like at this step, because we know G on Earth and we know omega on Earth, so you could have just gotten the length that way. Or you could just do away with having to solve for it, right? By doing like some kind of algebraic manipulation like this, which also works. And either way, you should find that it's 11.4 seconds. Cool. So number 18. Let's see here. Okay, so this one is like dead easy if you've seen this expression for the relationship between momentum, linear momentum, and translational kinetic energy, which you probably haven't, right? It's not something that's often talked about, but the idea is that we can write the translational kinetic energy of an object as the magnitude of its momentum squared over double its mass, right? And so we can just show that this works really quickly because P is mv, right? So when we square it, we just get m squared v squared divided by 2m, which is, of course, mv squared over 2, right? Which is the kinetic energy. So it seems like saying that the translational kinetic energy is P squared over 2m is fine. Now what we do is we just say something like K T prime, right, is going to be P prime squared over 2m, which is just double the original linear momentum, right? So 2 pi, we have to remember to square the whole thing, right? We're not just going to square the p and leave the 2, because that's not going to work. And so what we find is that this is 4 p squared over 2m, right? And then we just pull this 4 out in front. 4 is what we multiply p squared over 2m by. And this is just 4 times the original translational kinetic energy. So doubling the momentum makes the kinetic energy quadruple, right? And so like tripling it would make it, 9 times what it originally was, and so forth, right? So it just depends on the square, basically, of the factor by which you change the linear momentum. Cool. Somebody in chat is asking about, or in the group me is asking about one of these that maybe I'll just look at next. Somebody's saying number 7. He's asking if it's impossible, and I guess there's a chance that it is, right? Because I've made some mistakes, but I will just verify that. This one. Let me just tell him. Okay, so a mass m is suspended from the ceiling by a spring. It is gently brought to rest with the spring extended 0.1 meters beyond its equilibrium length. If it is set to oscillate after, what will the frequency of its oscillations be? So the idea is that when it's in equilibrium, the hook force, the magnitude of the hook force, yeah, I can do those. Hook force equals the magnitude of the gravitational force. So we could write something like this. We could write that K script L equals mg, right? So we want to solve for K here, because that's what we need for the angular frequency, right? Omega, remember it's the square root of K over M. Give me 1 second here, I gotta text somebody back. Okay, so then that's cool, right? And so we agree, right? Because I've talked about this, I think, a few times now, that nothing changes about the angular frequency when we're talking about oscillations in the vertical direction or the horizontal direction, other than sort of this shifting of the equilibrium position, right? But well, I guess I misspoke, but the angular frequency doesn't change, right? The only thing that changes is the shifting of the equilibrium position. It just is lowered a little bit. So what we do is we say, okay, the angular frequency is, as usual, omega equals the square root of K over M, and we just plug K in. So this is going to be square root of mg over ml, right? And so we find that it's just the square root of g over l. Which is interesting because this looks very much like the simple pendulum, right? But it's not the same thing, because here L is the extension beyond the equilibrium position. So I'm also telling this person that you don't need the spring constant in case they're not here. And so here we find, let's see what we got. Square root 9.81 divided by 0.1. I'm getting about 9.2 9.90 radians per second. Cool. Okay, so that was the one that was asked about in chat. Let's see, 22. Ah, yes, when you're standing on the Cathy of Learning, right? I love the Cathy of Learning. This is, I don't think this one is also too bad. It's just a little weird because it's weird to think about something going into orbit so low above the surface of the Earth, but I guess like providing it doesn't hit anything as it orbits, this is fine. So what we want to do is we apply Newton's law of universal gravitation in conjunction with the condition for uniform circular motion. So all we're saying, right, is that the net force in the centripetal direction on the ball is going to be GMM over the radius of the Earth, right? Because we're talking about the centers of mass here, so we need to think about the distance between the center of mass of the Earth and the center of mass of the ball. So we have to call this R plus H squared as opposed to just R, because like R would be, just saying big R squared in the denominator here would be just like the surface of the Earth at sea level. And we're a little bit higher, right? We're like 163 meters higher than that. And then we just say, well, this equals the mass times the centripetal acceleration. But remember that the centripetal acceleration is v squared over r, right? We could even write vt here for the tangential velocity, just to make that clear. And it's over r plus h in this case. We can clean this up a bit, because first of all, you'll notice like we don't have the mass of the ball, right? But that's okay because it's just common to both sides here in our expression, so we get rid of it. We get rid of that. Get rid of that. And also there's r plus h quantity squared in the denominator on the left-hand side and r plus h in the denominator on the right-hand side. So we can cancel a factor of r plus h. So this just becomes r plus h. And when we cancel r plus h over here, we just wind up with v tangential squared, right? So from this, we see that v tangential equals the square root of gm over r plus h. And this is going to be a very large number, right? This is obviously not a realistic problem, but I thought it was kind of fun. So let's see what we get here. G is like 6.67 times 10 to the negative 11th. The mass of the Earth is 5.97 times 10 to the 24th. And R plus H is going to be 6.38 times 10 to the 6th plus 163. The G times M divided by R plus H onto the square root. Yeah, so I'm getting about 7,900 meters per second. So obviously not realistic, but you know, it's still fun to think about. There's that. So 22, then the next one was 24, right? 24 is actually a GRE problem that I found that I think is pretty interesting. Why can't we say the kinetic energy equals the gravitational potential energy? Well, there's a condition for circular orbits, right, where there's like some relationship between there's some relationship between the kinetic energy and the gravitational potential energy in a circular orbit. So you could do it like that. I think that's okay. I forget what it, I think it's like the kinetic energy is like 1/2 the gravitational potential energy. Let me see if I can confirm that really quickly, because that's good to know. Okay, energy in a circular orbit. This, okay, so what they're doing here is basically they're saying the gravitational force equals mv squared over r. Oh, we could do this here actually. I don't know that I want to though. Let's just see what this says actually. I don't know, I'll zoom in so people can see this. But basically, okay, so what they're doing here is they're setting the gravitational force equal to the mass times the centripetal acceleration, right? Which is v squared over r. Pretty similar to what we did. Then they're multiplying both sides by r, so you get mv squared over here. And then you lose a factor of r in the denominator over here, right? Now this mv squared is basically double the kinetic energy, right? Because kinetic energy is 1/2 mv squared. So they're just taking this equation and they're multiplying both sides by 1/2. And so what we could say is we could say that the kinetic energy for a circular orbit is 1/2 the absolute value of the gravitational potential energy for a circular orbit. Because this should be negative, right? If they were being no, actually, what they wrote is fine. But this right without the 1/2 in front is the positive of the gravitational potential energy, right? Because remember, it's written with a negative sign out in front. But yeah, so you can say that for a circular orbit that the kinetic energy has to equal 1/2 the absolute value of the gravitational potential energy, and that's fine too. You could have done this that way as well, right? If you knew that. Good question. Okay, cool. So 24 was the next one. This one's also kind of weird, but I think this is a good one to think about too. So I think we only have to focus on block B here, right? So focusing on block B, we just write out the net force equation in the x direction, right? And if we imagine sort of this happening in real life, and we just sort of like block A with our hand or pretend it's not there, what we would see is we would just see block B accelerating to the right at some rate, right? And so what we would have is we would have essentially the only force acting on block B in the x direction is the force of static friction. So in this case, the force of static friction is making this thing move to the right. And we would just say that this is mb times A. Okay, now actually I think we do have to look at the other block. We have to look at A. I feel like I might have missed something here though, because otherwise this actually doesn't make sense. Let me see if I can dig this GRE problem up. I thought I copied it exactly, but maybe I missed something, which I would be upset about, but Maybe we don't. See, these practice GREs like are good, but most of the I think this was the one. Most of the questions are like will like also involve like quantum mechanics or like electricity and magnetism or like, you know, weird stuff that obviously isn't relevant for this class. Oh, right. I didn't put the acceleration, so that's probably what messed you up. My bad. It's supposed to be 2 meters per second squared. In which case this becomes, I think, pretty straightforward. So I apologize for forgetting to put that in. Because what we see, right, is that the maximum static friction force is just going to be given by mu sub s n on B, right? MB A. Therefore, we could write this as mu sub s mBg equals mBa, and the acceleration divided by g gives you mu sub s, right? So it should be like 4.9. Oh wait, we want the, oh Jesus, we want the force. I'm sorry, I'm making this way more complicated than it needs to be. It seems like we don't even need the coefficient. Is it really just multiplying the mass times the acceleration? Is that what we're supposed to do here? I think it is. I think it's just multiplying the mass times the acceleration. And we don't really need any of the information except for the mass and the acceleration. Because like what would any other X force that could act on this block be, right? There's really no other force in the X direction on it. So we didn't need this, although it is given in the problem statement from the practice GRE that I found. And it should just be 10 times 2, right? So 20 newtons. Okay. Yeah, I apologize for leaving the acceleration out of there because you did need that. Like so I included what you don't really need and I didn't include what you do need. Classic Rye guy, right? Okay. Are there any other questions about this? Anything else people want me to look at? Well, I can just go through these one by one then. Let me just respond to this person asking about this number 7 one still. All right. So Number one, okay. What we do is we just think about the gravitational force on an object at the peak of Mount Everest. So we can say there's some effective gravitational acceleration there. So what we do is we write mg prime equals, and we just use Newton's law of universal gravitation again, g big M over the radius of the Earth plus the height above sea level squared. The m's cancel, so we find that g prime is simply g big M over r plus h squared. I don't remember any of these numbers, so let me just do this. And I'm finding it's about 9.76. So 9.76 meters per second squared. We want the ratio. So we just take g prime over g, right? So when we divide this by 9.81, we find that it's about 0.994, let's say. So it's pretty damn close, right? It's like you wouldn't even notice. But there is a difference, technically. Why is that prime so weird? Why does it keep... Oh, okay, whatever. All right, number two, your friend is standing. This is pretty similar to the exam question, right? So we could probably knock this out pretty quick. We just want to say that basically the initial angular momentum is just going to be, sorry, I keep doing this. The initial total angular momentum is just going to be the orbital angular momentum, right? The final total angular momentum is just going to be the spin angular momentum. And here, this is going to be, this is just RMV, right? Because I said in the problem statement that it has a trajectory that's tangential to the edge of the merry-go-round, right? So we're used to having the sine of theta term in there, but in this case, sine of theta is just sine of 90 degrees, which is 1, right? So this is all we have for the initial angular momentum. Final angular momentum is a bit trickier because we have to adjust the moment of inertia to account for, well, everything, right? Because there is, let's see here. There is, I'll call this I prime, I guess. There's the moment of inertia of the merry-go-round, right? Then there is the moment of inertia due to your friend standing there. Then there's the moment of inertia due to the ball now being in your friend's hands, right? Like this. And then this, so that's the moment of inertia. So then you just have to multiply this all by omega to get the spin angular momentum here, right? So what we do is we make Mathematica solve this. And Mathematica doesn't like the big I. It takes that to be the imaginary number, so I have to use iota, but that's fine. Solve this for omega, as the British people say. And we plug the numbers in. So little m is 10. Big M is 70. I is 200. And this isn't going to be very fast if I remember correctly. V is 15. We need R. R is 1.5. So about 0.6 radians per second. Let's say J naught being equal to J final implies that omega is approximately 0.592 radians per second. Why can't we say the mass of the person is just plus 10 and use that as my M? The mass of the person is 70, right? The mass of the ball is 10. So we have to, we could just put them together and say it's 80. That's fine, right? That's what we did here essentially. But it would be a contribution due to the 80 kilograms total, right? Because this is 70 times 1.5 squared, and this is 10 times 1.5 squared. So we could write, if we wanted to, maybe this is what you're saying, we could write something like this. We could write maybe big M plus little m r squared. That would be fine, right? It's just algebra, just factoring out the r squared. But I mean, the thing is that your friend is standing at right at the edge of the merry-go-round, right? And your friend catches the ball at that same point. So the ball and your friend are 1.5 meters away from the axis of rotation. And so you have to account for both of their contributions to the moment of inertia here, right? Because they both have a non-zero distance from the axis of rotation, and they both have non-zero mass. Does that make sense? Oh, okay, maybe there's just like a, let me just double check my work here. So we said RMV equals all this times omega. This is good. I think this is fine. Yeah, I don't know. You maybe just try it again. Maybe something went wrong with the calculator. But I'm not seeing a mistake here. Let's see what else we got. Number 3 I talked about, right? And I think that this is a fairly challenging problem. So like, I don't know, if it doesn't make complete sense, I wouldn't stress it too terribly much. I can do 11, I think. We'll see what it's asking. Yeah, so I don't think should be too bad. So we just want to compare, essentially we just want to compare the initial and final mechanical energies, right? And then realize that the only non-conservative force doing work here is the drag force, and realize that the work that it does has to account for the difference in the energies. So the initial mechanical energy is going to be 1/2 m v naught squared plus mgh, right? The final mechanical energy is going to be, well, it doesn't have gravitational potential energy because it lands on the ground, and we're taking the ground to be our y equals 0. So it's just 1/2 mv squared. And like just because maybe this would be illuminating, we can get numbers at this point. Because we want to see that essentially we want to see very clearly that the drag force is taking energy out of the system, right? So E naught is going to be 1/2 times 5 times 42 squared plus 5 times 9.81 times 10. So this is let's keep it exact. It's 4,900.5 joules. And then we get a number for this. 1/2 times 5 times 43 squared. And this is, and we see that it is losing energy, right? Because this number is 4,622.5 joules. What did I say? Wow, I'm losing my damn mind. 4,622.5. Okay, 22.5 joules. So then the work done by the drag force is going to be delta E, right? Which is just E final minus E initial, which should be this minus this. And it's gonna work out to be negative. Why is it doing this? What's going on? There we go. It's about negative 278 joules. And that's what we would expect, right? Because the drag force basically can only do negative work because it's always opposing the instantaneous velocity of the projectile, right? So it's just comparing the initial and final mechanical energies and then noting that the difference must be accounted for by the work done by the drag force. All right. Who else has something they want me to look at from this, or anything at all, I guess, really? If nobody's got anything, I'll just keep going with what were you on, like number 4 maybe? Number 15. Draw the triangle. Yeah, so what I was trying to say was that you're going up the hill that looks like this, and it makes some angle theta with the horizontal, right? And you want to solve for, let's call it L, the distance along the surface of the hypotenuse of the right triangle that you go, right? So you would note that your height, right, because this is important for your gravitational potential energy, can be related to the angle and the distance you go up the triangle, right? Is this good? Do I need to say more about this? I guess I will just say really quickly in case it wasn't clear. Hopefully it was, but like when you're going up the triangle or up the hill, the force that the wind applies is horizontal, right? So it looks like this. It's not directed along the surface of the hypotenuse of the triangle, right? So this is like the force that the wind applies on you. So it's like a little bit more complicated than if obviously the wind were blowing up along the direction of the slope, right? The wind triangle. Okay, so what we want to do is we want to make this into a right triangle. Like this. This is the angle, right? This is also theta. Because we're just breaking it into its components that are parallel and perpendicular to the slope of the hill, right? So what we care about is this component here. And we could call this F W, and then I would put like two vertical lines here to indicate that it's parallel, right? That's what we want to do. Yeah, cool. Just note, in case it wasn't clear, it probably is, but this is our right angle here. This. So you just have to be careful breaking this into its components, but if you see that, it's probably fine. Number 7 from the other one, let me see. I think, let's see what we got here. Yeah, this one's not so bad, I think. I'll just go to the bottom of this document. So the idea here is that the friction force is what is preventing you from sliding out, right? And so that is our centripetal force in this case. And the question is maybe like, well, is it kinetic or static? And that's a good question to ask because we're given both coefficients, right? And so I am just going to say that it's static because basically you're not sliding out and you're not moving closer towards the center of the circle. So basically there's no relative motion between the tires and the ground in the centripetal direction, right? Because you're maintaining that circular motion. So it should be static, and in general you will have that the static friction is what causes circular motion in like highway curve problems like this. Right? So what we do is we just say the force of static friction must equal mv squared over r. Now, because we're talking about your car being right on the verge of sliding out, that means basically we're discussing the maximum static friction force, which means we can just write that this is mu sub s times the normal force, because static friction is usually defined in terms of an inequality, but because we're talking about the maximum value here, it's okay to write it as an equality, and this equals mv squared over r, just from the uniform circular motion condition. Now, the normal force is just mg in this case, right? So we find that the mass is going to cancel out, which is good because it must. We don't have a mass here. But if you could make one up, I guess, if it makes you feel better. I think I've done that before. And what we see is that v squared should equal mu sub s g r, right? Therefore, v equals the square root of mu sub s gr. I forget what the number was here, but we can calculate it pretty quickly. Twelve meters per second, so it should be C, right? I'm curious about something. No, okay. I just wanted to see if you accidentally wrote r squared, if that would be like one of these choices, but it's not. I'm a little surprised, actually. So that, yeah, cool. Okay, let's see. If there are no questions, I'll just maybe do a few more of these before I end. It's been a long week, my friends. It's been terrible. I think you all understand. I think 8 is good. So what we have to do here is we have to figure out what the moment of inertia of the rod is. This is simple because we have a ready-made formula for this, right? So the moment of inertia of the rod is just 1/3 ml squared, if I remember my moments of inertia, which is questionable. I'm just making sure. Why is it so hard to find this damn formula? Like, I'm 99% sure it is just 1/3. Oh, I'm wrong. Wow, okay, it's good that I checked. It is 1/12, so 1/3 is about the end. Okay, cool. Glad I didn't just decide I was right and stop checking. Oh, that's good. Okay, and then we have to do the parallel access theorem for the sphere, right? Axis. Would they have to tell you if it was parallel or perpendicular? Well, because of the symmetry, it actually doesn't matter, right? Because kind of no matter how you rotate like a stick that has a ball at the end, it's gonna sort of look. Yeah, I guess technically, actually, they would have had to tell you that it's perpendicular to the length of the rod. That's a good point. Now that you mention it, but it doesn't matter which way it passes through, right? Let's just say perpendicular to the length of the rod. Writing questions is tough, guys. am really learning that. So, but now that we've gotten that out of the way, right? We can do the parallel access theorem for the sphere, but I do need the moment of inertia of a solid sphere. I think it's like 3/5 mr squared, but I don't remember. Let me double check this. Oh, this is handy. On Wikipedia, they have like a table. 2/5. Okay, I was close. I was pretty close. So remember, parallel access theorem says that it's that the moment of inertia is given by the moment of inertia of the object about an axis passing through its center of mass plus the parallel axis term, right, which looks like this, and d is the distance from the old axis of rotation to the new axis of rotation, right? So it's the distance from the center of mass axis of rotation to the axis of rotation we want to calculate the moment of inertia for, right? I can do number 22 after this. So what we find is like the moment of inertia about the center of mass we just found was 2/5 mr squared, right? I just looked at this lovely table that they have here on Wikipedia. Wow, some of these are awful. Yeah. And then we have to add the parallel axis term. And so basically, like I was just saying, this is the distance from the center of mass axis of rotation to the axis of rotation we're concerned with. And in this case, it's going to be 1/2 the length of the rod plus the radius of the sphere, right? So our total moment of inertia, let me put an S here for sphere. Total moment of inertia then is just IR plus IS, which is this plus all this crap, right? Let's see. I guess I'll try to get a number for this really quickly. Why not? So 1/12 times 1 times 0.5 squared plus 2/5 times 0.5 times 0.1 squared plus 0.5 times 0.5 over 2 plus 0.1 quantity squared. Let me just double check this. 12 times 1 times 0.5 squared plus 2/5 times 0.5 times. I think this looks good. So it's rather small. It's like 0.084 kilogram meters squared. Number 22. Did you want it from the Hattridge practice final or the other one, the one that I did? Okay, cool. Let's do this. 22. Yeah, so I already actually did this one. I'll just talk about what I did. And somebody else had another way of doing this, which I thought was pretty cool too. But what we say is that in this case, we just demand that this thing is undergoing uniform circular motion, right? So remember, uniform circular motion, we just write that the MA part of Newton's second law is mv squared over r, right? And so I just put a v here, or a t here for the v to make sure that it's clear that it's the tangential speed that we're talking about. And so this was the right-hand side. This is our MA term, basically, where this is the centripetal acceleration. And then this is just the force on the ball according to Newton's law of universal gravitation. And we just did the algebra, right? We saw, for instance, that like the masses canceled. So the mass of the ball, which is little m, cancels from the left and the right. So it's common to both sides. So we wind up with this. We wind up with, well, actually, and a factor of r plus h cancels out too, right? Because you have r plus h quantity squared here in the denominator on the left and r plus h in the denominator here on the right. So what we find is this, right? And it works out to be some really, really large number that you could never realistically throw a ball at, but that's fine, right? It's just kind of something to think about. So it should be about 7,900 meters per second. That's what we found. Cool. Okay, I probably have time for just like a couple more here. If anybody has anything in specific they want me to look at. Number 18. Yeah, okay, yeah. And that's what somebody else was asking, why can't we use the gravitational potential energy? And we can, right? There's this thing, that this relationship between the kinetic energy and the gravitational potential energy for a circular orbit, where uh the kinetic energy is 1/2 the absolute value of the gravitational potential energy. So you could have just done that too. I think that's also fine. So two ways to do it, right? Okay, so number 18. Oh yeah. So this one is really not bad at all if you just realize that the translational kinetic energy of an object can be expressed as the square of its momentum over double its mass, right? And I show you why this works because you just write out what P is. It's just m squared, or P squared is m squared v squared, right? And then you cancel a factor of m and you just wind up with mv squared over 2. So I think once you realize that, it's pretty straightforward. You just, write out that P prime is double the original momentum. And so when you square this whole term, you get 4p squared. You just take that 4 out in front. This was your original kinetic energy, your translational kinetic energy. So you find that it's just 4 times what it was originally, right? Yeah, so not so bad if you've seen this little trick, right? That I don't think they really talk about very much. Okay, anything else? Anybody else got anything? That was pretty fast, so. Yeah, it's a good question. I would say some of these, like I would say that there might be like 1 or 2 questions on the final that are like comparable to this one here, number 3, for instance. Maybe this is harder than actually any question on the final, in my opinion. But I think this is a pretty good approximation. I mean, the style's a little bit different because different instructors will have different ways of writing their own problems. And so I don't know. I think it's like on par basically. Who else has a question? Anybody got anything? 18 again. Let's see here. Yeah, we can talk about this. So let's just focus on this part, right? So I'm just going to tell you that the translational kinetic energy of an object can be expressed in terms of the magnitude of its linear momentum, right? So we write that k equals p squared over 2m. Now, remembering, right, that p is just mv, or the magnitude of p is just mv, we see that when we square it, we get m squared v squared on top here, right? On top of this fraction, which is just mv squared over 2. This is just the kinetic energy, right? So this line here is just to convince you that we can go back and forth between the magnitude of the momentum and the kinetic energy with this relationship, the translational kinetic energy, right? So if we believe that, then all we do is we say, well, what happens if we double the momentum, the translational momentum of an object? Just somehow we're able to do this instantaneously, let's imagine. So we call the new momentum P prime, right? And we write that P prime is just double the original momentum. So when we square this whole thing up here, we get 2 squared times P squared, which is just 4P squared on top. And then we just take the 4, we're just doing algebra, just rearranging this thing. At this point, we just pull it out in front. And we realize that what we found was 4 times P squared over 2m. But that was our original kinetic energy, right, from this equation. And so then we find that the new kinetic energy is just 4 times the original kinetic energy. So basically it quadruples, right? When you double the linear momentum of an object, its translational kinetic energy quadruples. If you triple, right, the translational or linear momentum of an object, its kinetic energy is multiplied by 9 and so forth, right? So it's just proportional to the square of the factor by which you're changing the linear momentum. Is that helpful? Does it make sense now? Cool. Okay, let's say one more. Who's got something? Anybody? Okay, nobody else say anything. Let's see, 8. Oh, we just didn't, or did you want 8 from here? Which one? Which 8 are we talking about? Nine. Okay. So yeah, so what we want to do here is we could derive this, but we don't have to because it's something that you know is well known, right? That for a mass oscillating horizontally without damping, the total mechanical energy is E total, and this is just 1/2 K times the amplitude squared, right? So this is the total mechanical energy at any time, right? No matter where the mass is. So with this in mind, we can say that when the block is at a distance d away from the equilibrium position, the energy is 1/2 k d squared, right? This is the elastic potential energy plus 1/2 m v squared. And we just say that this is always equal to 1/2 k a squared for this kind of a situation. So we just do the algebra, right? I'll make the computer do it because I'm tired and over doing algebra. Not because of you guys, just in general. We solve this for v, right? V is what we want. These are the exact same answer. One is just negative, right? So I'll just make it plug the numbers in for me. A is 1.6, D is 1, M is 2, and K is 180. And we find that it's like 11.8 meters per second. And there you go. Okay, I will end it here. If on a scale of 1 to 10, how hard is this final going to be? Let me look at it real quick, I guess, and just see. Well, elastic potential energy is just 1/2 kx squared in general, right? And so we're just using that. If you tell me, I don't know, like how hard did you think Hatridge's second exam was on a scale from 1 to 10, just so I can get an idea. I don't know, then maybe like a 6. I don't know. I think that there's some tough questions in here. And I would prepare, or I would be prepared to go in there and and take it very seriously, I guess is what I would say. I think that this exam is maybe a tad bit harder than the practice exam that Hatridge gave out. There's a few on here, honestly, that are pretty challenging. And then I think a few that are like dead easy, and then the rest are pretty much in between, like middle of the road. Yeah. Okay. I don't think there are any problems really that are trying to trick you. But just remain vigilant, as always, right? Yeah, happy to help. No problem. Just feel free to reach out if you need anything between now and then. I can potentially try to get to the location just like a little bit earlier than the start time if anybody has any last minute questions, I guess, depending on like what time I get up and stuff. But yeah, just reach out. I'll see you all tomorrow. It's gonna be fun.